I was bad mathing it, and it started recording from the get-go. Okay, when we talked last week, I said, I wouldn't mind doing like a chapter review, module review, as long as it wasn't me lecturing more, because I could just do that in 1 week and be done with it. I was looking more for discussion. Hopefully, people have gotten to read, if not all this stuff, most of it. And so rather than me sitting here and talking the whole time, I could ask questions and we could discuss things and maybe provide a little clarity. Something I did this week, just so you're not staring at the same blank screen, I went through because on the book website, there is a bunch of PowerPoints. And so I cobbled through all the different PowerPoints looking for the different topics that were listed in the module. And it's not, sometimes it doesn't always look great, but it's probably better than looking at the blank screen, like you did last 2 weeks, looking at this the whole time or something else, the overview and stuff. So anyway, I'm going to kill my camera. Yes, I do want to share. And then I want to turn off my camera just so we can save bandwidth and maybe get through this without totally cratering. Okay, so take it, nobody has any questions. We got 5 out of 26. That'll work. And again, we are recording, so we'll have that for everything. Let's talk a little bit. First, a little review of some of the things we went through last week, talking about the errors, type 1 errors and type 2 errors and significance levels. And I'm going to kill my author notes there. When we're talking about errors, what are we talking about with a type 1 error? Anybody?
It's about rejecting the null hypothesis.
Yeah, you're basically making a mistake and you're rejecting a true null hypothesis. The null hypothesis is correct. There is no significant difference, and you reject it saying there is a difference. Okay. Conversely, the type 2 error would be the exact opposite. Okay. You're failing to reject a false null hypothesis. Alrighty. Basically, there is a difference, and you're saying there isn't. Then you go to significance levels. What is the standard measure? Well, I'll say standard measure because the one most often used, the significance level in the statistics we've been looking at. Anybody?
The p-value?
P-value, yeah, that's good. Basically, and that's stated at p at the 0.05 level. Now, when they say, it's P at the 0.05 level, or they don't say point, they just say P at the 0.05 level. What are they talking about? Are they talking about, what are they talking about when they say the significance level is at the P at the 0.05 level?
Because it's probabilistic, you're basically saying only about 5% of the effect or less, hopefully, might be due to random chance. And
that's it.
The rest is your model.
Yeah, it's the influence of your treatment. Now, that's real important to look at when you're looking at P. Now, normally you'll see, most of the time when you look at something, they'll go ahead and state it P at the 0.05 level. Occasionally, you'll see somebody who has even more confidence in their data, and they might go below that. If you go above that, you don't generally see that because that means there's a whole lot more error. I'm not saying it never happens. I guess depending on the type of study you're doing, you might be willing to allow for more randomness in your study. But generally, it's 0.05 or less. And don't forget that 0 when you're looking at stuff, because a lot of times people will state it as 0.1, which sounds that's kind of low, but you realize that's actually twice as much as what is acceptable. So when you're looking, when you're looking at,
sorry about that.
That's okay. When you're looking at significance levels, look at that very closely. Make sure that 0 is in front of that 5 or 0 is in front of anything, because if there's any number other than 0 in front, it's probably not really an acceptable or a significant, acceptable significance when you're trying to consider random chance affecting things. Okay, again, type 1 error is false rejection of a true null. Type 2, failure to reject the false null, and the significance level P at the 0.05. The outcome would be 5 times out of 100. Okay, now basically when we talk statistics, we're talking different things you can use to describe and organize and interpret data that you collect. Now there's 2 types of statistics we deal with. One is called descriptive statistics and the other is inferential. What's the difference? Anybody?
Um,
It's okay to guess.
you told us last week, and I can't remember off the top of my head.
Well, let's look at the words they're using here. Okay, first of all, they're talking about descriptive statistics. Okay, and when you're talking about easy for me to say, descriptive statistics, basically you're talking about things that describe. Okay, you're providing a description. Sometimes you're organizing particular characteristics of a data set. Okay, so when you're describing, organizing, interpreting information of a data set, that's what you're doing when you're using descriptive statistics. Okay, we just answered that. Okay, there's what I just told you there. Organizing and describing. Now, a lot of times you'll hear people refer to data sets. Other times you hear people refer to data. It's all the same thing. A data set is just the collection of data. It's the set of numbers, columns, results, whatever, test scores. Data is the same thing, just for some reason. Statisticians like these fancy words. So anyway, when they say data set or data, they're talking about the same thing. Okay, some examples. The average age of everyone in this class, that describes something that's happening. The most common grade on this week's quiz, that would be something that's happening. Okay. On the other hand, you have inferential statistics. Now, what are you doing when you're making inferences?
You're drawing conclusions.
You're drawing conclusions. You're making assumptions. Is more accurate. Yeah, you're saying, well, based on what I see here, I'm going to assume this is something else is going to happen. Okay. And again, basically, whenever you do a survey, you don't generally deal with a whole population. You deal with a sample. So you're taking that smaller sample and you're saying, okay, that subset of that population, and you're saying, okay, what happened to this sample, I think is also going to happen to the entire population within a certain degree of error. And so you're making inferences. You're saying this happened here in our study, and we're going to assume, or we're going to infer that that same thing would happen amongst the general population, whatever that characteristic is. Okay, some examples here. You take 100 people with depression and split them into two groups. One group gets a placebo, a sugar pill. The other group gets the new wonder drug, and then you find that it's a statistically significant difference in improved mental health among the people who took the drug. Okay, so you're saying, okay, if among these 500 people we gave the drug to and 95% of them improved, we assume that if we unleash this drug on the general population, 95% of the people who suffered from depression would also improve. And so basically you're forecasting based on what your study revealed, as opposed to describing or reporting as the descriptive statistics would do. A lot of what we deal with and what this chapter deals with what are called measures of central tendency. And of course, being statisticians, they want to define as much as possible, and two, they want to use terms as confusing as possible. Let's put it that way. A lot of times they talk about averages. Now, when you and I think of an average, we think of like a batting average or an average of a class, and test scores and things like that. But in the book here, when they talk about averages, basically they're talking about measures of central tendency. And we've talked about three general measures of central tendency. And what are those?
Mean, median,
I remember the mean, the median, and the mode.
Yeah. Okay. And yeah, that's what we generally deal with, because they describe a whole lot of what is going on. And when you want to just get a quick idea of what results were on a test, on a survey, on a study, these three will give you some great information. But they'll give you different types of information. If you don't use them properly, you can run into trouble, and you can have some very inaccurate studies. Now, the mean's real easy. It's the arithmetic average, and you all done averages for. You take, here, just go here, the entire set of values, compute the sum of all the values, divide by the total number of values, total frequencies. That's real easy. Now, things to remember when we're dealing with some of these formulas we're going to deal with tonight is what all these little symbols mean. starting off with N, when you have the capital N, that refers to the whole population. That means everybody, the entire 5th grade of the Dallas school district, as opposed to the sample, which is, the 5th graders at Jones Elementary. Okay, so large N is the entire population, small n is the sample. Now, a sample mean is a measure of central tendency that they will use to infer to the population mean. It's also referred to the, that's easy for me to say, arithmetic mean. And basically, it's the center point of all the values, okay? Now, the nice thing about mean, it gives you a real quick snapshot, so to speak, of where the class is at. The downside is that an extreme score can throw things off. You always, when you're in grade school, the teachers handing back the tests, and people are getting in the 78 and 83 and 79 and 80, and then all of a sudden one kid gets like a 95. And everybody hates that kid's guts because he or she has thrown off the class average and shown the teacher what's possible in that test, and makes everybody else look, like maybe they didn't study well. So mean is very sensitive to scores, and that can skew and distort your findings. Now there's another thing called a weighted mean. What is that? And I perfectly allow guessing. Yeah, weighted mean.
Is that where you drop the high-low?
No.
Either that or some of the scores are weighted, right?
Well,
to count as more.
Yes, but probably not in the way you think. I know if you ever worked with Blackboard, they had like weighted scores. Basically, this test was worth more than the other test because maybe it was not necessarily that it had more questions or worth more points, but it had greater value. Maybe they counted it 1.5 times rather than make a test of 15 as opposed to all the other tests that had 10 questions. They made it 1.5 times the value of the others, and then that's a weighted score. Here we're talking about weighted means. It's basically a way of making things easier when you have a lot of data to work with. Okay, here's an example here. Say you do a survey or have a test and you have a class of 100 students. Well, adding 97 4 times isn't that bad, but you adding 94 11 times, all the rest of the thing. Do you really want to have to add a column of 100 numbers? Probably not. So what you do is you set up a table like this, and you take whatever the values that appear, and you take their frequency and come up with a sum. Then you add those sums, divide by the number of values you have, and you will get the exact same numbers if you stood there with a long column of numbers and then divided that by the total number of entries. Does that make sense to everybody?
So in this case, do you take that 8967 and divide it by what, like 8?
No, you divide it by 100.
Oh, by 100. Oh, okay, I gotcha.
Yeah. You get the same result as if you took that long column of numbers. This just is a little easier way of doing it. Something like this, you probably won't ever report, in a study. This is just a tool to help you not have to deal with a column of 100 numbers and add it. Okay, so this is just a tool more than something that you would put in a report.
So if your total in that second column came out to like 53, then you would divide that 8967 by 53.
Yeah, if you had 53 different test scores you were doing, whatever that is, that frequency.
The frequencies.
Yeah, this is a real simplistic example because they conveniently did it by 100. But if you had 53 students, you had 53 test scores, and they broke down. Some got 4, some test scores appeared 4 times, some 11, some 12, or whatever. You just divide. It's basically a way of making it simpler, so you're not sitting there with a huge column of different numbers and trying to remember to carry the one when you add.
So it's the exact same then as the arithmetic mean, except it's just a faster way of calculating.
It's just a faster way when you have a lot of numbers.
Okay.
And if you're using Excel, you can put the numbers and the frequency, and it'll, set it up all for you. Or you. Is
there a formula in Excel for weighted mean?
Not for weighted mean. Basically, what you do.
It would just do the average on it.
Yeah, you'd have like the value column is A, the frequency column is B, and the value times frequency is C. So in that first row, you'd have sum equals A2 times B2, and then you just click on that and drag it down. So the next one would be sum equals A3 times B3, and if you were going to do that. But again, this is not something you'd report in a study or a journal article or anything, but just it's a tool you can use so you're not sitting there with those long common numbers and having trouble remembering where you were on that. Does that make sense to everybody?
Yes.
Okay. I think. Cool. Moving right along. Okay. Again, I'm not going to go through this. We already did, but if you need to refer back to this, you'll have it on the recording. What I might also do is send this PowerPoint out to people too, so they'd have that. Okay, let me make a note to send PowerPoint.
Thank you.
You're welcome. Yeah, I'm sorry I didn't use his PowerPoints earlier, but the first week I barely got into class and I was on the road, and last week I had just gotten home and was still scrambling to get things organized and stuff. Okay, moving on to the next central tendency, indicator central tendency, and that's a median. Now, what is that? Anybody?
It's the middle score. If you line them up in order, it's the middle score.
Yeah, it's the middle score. Basically, it's where half of the remaining scores fall above and half fall below. Okay, and here's a list here showing higher to lower, and there's 5 values. The middle score here you see is the 37,668, and that's your median. Now, of course, this is really convenient because there's an odd number of entries, and it'd be nice if you could control all your studies so that you had odd numbers of subjects, so that you could always get an odd number. But that's not always going to happen. Sometimes you can have an even number. What do you do when that happens?
You average the 2 that are in the middle.
Average the 2 in the middle, yeah. You take those, you get their mean, and there you have it. You have 36,084. Now, what happens if the 2 in the middle are the same number? They're both 37,668.
Then there's not really a need to do the average because they're both the same. So it would just be that.
That's it exactly. So really easy to do. We already answered that.
Still the mean of those.
I'm sorry?
That would still be the mean of those 2 put together, though, right?
Yeah, exactly. Well, they're the same number. So the mean of 25 and 25 is 25. 25 divided by times 2 is 50. Divided by 2 goes back to. So yeah, it's basically those 2 numbers, however they are. All right, moving finally on to the mode. That's something that sometimes we don't see used, and we often see it used incorrectly. Any
Isn't it the one that occurs the most often, like the scores with the most frequency?
Exactly. And that comes in handy in different situations, and we'll look at that in just a second here. Yeah, the mode is what happens most frequently. Now, on one side, it is the least precise measure of central tendency. And you can have more than one mode. If you have 2, it's called bimodal. If you have more than 2, it's called multimodal. And that happens, I'm going to say it happens a lot, but it's not rare, but it can happen.
Is that where the different scores each happen the same amount of time?
Exactly. You have test scores from 60 to 100, and 75, 87, and 93 all appear 8 times. Okay. And it said some people get upset. And there's nothing really to get upset about. It's perfectly acceptable to be multimodal or bimodal or anything else modal, as long as you accurately describe the most frequent value that appears, whatever it is, whether it's a 1 value on its own, 2 or 3, however many. So yeah, you're good either way. And again, steps to finding the mode: list all the values, tally the number of times each value occurs, and the value occurs the most is the mode. And we'll get into something similar here in a moment when we start talking about some other types of ways of depicting this visually. One of the most important things, before I forget to tell you, when I first took my first statistics course, which was scary, the instructor pointed out that, we all think of statistics as numbers and really heavy duty numbers, and there are numbers involved, of course, but he said that statistics is just as much a visual concept as it is a numerical one, because a lot of times, you can understand the visuals a lot easier. You can understand the numbers. Now, the nice thing about numbers is they give you very specific and granular data. Okay, if you need to know to the 20th decimal point what something is, those numbers are going to give it to you. Whereas a graph that expresses it, you probably wouldn't be able to discern that 20th decimal point. The nice thing about a graph or a chart, it gives you an instant snapshot. It gives you an idea of relationships, of conditions that exist, and we'll show you that in a second. And so it's very cool, because a lot of times if you just need an idea, okay, is A more important than B? Well, you see the chart where A has a real tall column on it and B has a short one. You can instantly see that A is more important than B, and maybe you don't need to know the percentages or the numbers or the scores or whatever. But anyway, I digress. And finding the mode, basically the value that occurs the most is the mode. When do you use what? This is important. Now, you use the mode when the data is qualitative, when you're setting up categories, Republican or Democrat, red or white, English or Spanish or something like that, and the values fit into one category. Now, a lot of times people make mistakes. They'll treat modes, this is nominal data. It's a category. It's this or it's that. Sometimes you'll see people try to turn it into ordinal data, meaning putting it in order, or even ratio data, trying to establish, levels of relativity between the different scores. Mode is all it is nominal. It's going to be this or that. It's like if you were to ask 100 women, are you pregnant or you're not pregnant? And say 75% of the women were not pregnant. You couldn't say the mode is that, the whole group of women are a quarter pregnant, but you'll see in stuff that gets published, the mode being used that way. Maybe not in reporting, how many women are pregnant, but you'll see it being misused as something other than this category and that category. And again, just because it's published doesn't mean it's good. It doesn't even mean it's factual or valid or reliable. Median is when you have extreme scores, because again, like I was talking earlier, with the, you get your test results in 7th grade, and the whiz kid sort of messes up the curve by getting a 95 when everybody else got a 70 something. So the median will offset that, because it's going to show where that center point is in all the scores. And even if the kid has 100, and he's the only kid with 100, he's only one score out of the whole class, and it'll be offset by the total number of participants above and below that median point. And then using the mean when the data does not include any extreme scores, which are referred to as outliers. And so that's basically a quick rule of thumb on when to use these different things. Okay, when we were talking about qualitative and quantitative methods, we were talking about theories. And what did we call these two? One is for doing what with theories, and one is for doing something else with theories. Any guesses?
Qualitative is theory building, quantitative is theory testing.
Right. Qualitative is theory. Let me talk with it. Okay, qualitative is theory building. Okay, this is where you're taking information from people. It can be numerical data, but a lot of times you're getting opinions, you're getting general tendencies, people's perceptions and things like that. And then you take these things and you code them and you analyze them and say, well, based on what our surveys indicated, we think this is going to happen. And then you go ahead and put together a hypothesis, and then you start doing quantitative methods where you're taking numerical data and establishing it to prove or disprove your hypothesis. So again, qualitative is theory building, quantitative is theory testing. Okay, moving right along here. I'm glad we're going rather quickly, because when I put this together, I was shocked, because I think I have I have 101 slides. So I'm glad we're moving rather quickly, because I didn't want to be here till midnight, and we're barely into a half hour here. Okay, variability, what is that? Anybody?
Isn't that how far the scores are from the average? Like, how much does your test vary versus how much all of them resulted in the same thing?
Yeah, basically, it reflects how scores differ from one another, specifically from the mean. Um, so, yeah, well, I think I probably published, yeah, variability, again, reflecting how scores differ from the mean. It's also called spread or dispersion. Now, this can be very important, and a lot of times you'll see the mean and variability reported this, together in a survey, because the mean will tell the average, but the variability will show how much above and below that average the scores appeared, and in different ways. One way is the range, one way is standard deviation, another one is variance. And as I said here, typically you report average and variability together to describe distribution. Now the range is real simple. I think it's real simple. If I can understand it, it must be. What are we talking about when we're talking about the range?
Isn't that the spread between the two, the high score and the low score?
Yeah, basically it's the high score and the low score. Oops, let me see here. And here's computing the range. And basically, normally what you'll see in studies is what is called the exclusive range. Take the high score, subtract the low score, that's your range. You know, the high score was 97, the low score was 50, the range is 47. Now they have something in the book they refer to as the inclusive range, and that's basically the high score minus the lowest score plus 1, which in my example would be 97 minus 51, in which case your range is 46. I can't remember any time I've seen an inclusive range, but sometimes statisticians they'd rather err on the side of caution, and they'd rather be more inclusive of something than less, and so they'll sort of limit factors or maybe change factors to allow for something that might be a little bit more precise. And that's the best way I can describe it. I can't necessarily say there's a logic to it. I imagine whoever invented inclusive range, I should say, had a reason. But as I said, most of the time when you're looking at ranges in journal articles, you're looking at that exclusive range, whereas your high versus your low, and that's what they report. Okay, here's one you're going to see a whole lot of, and we're going to spend a little time on this one: standard deviation. Okay, you hear about that in almost any type of report. They'll say the standard deviation is this. And so what do they mean by standard deviation? Or what is meant by standard deviation?
Isn't that where most of your scores fall within one deviation away and then two? And it gets into that like 95%, 99%.
Yeah, but away from what?
From the mean or the middle.
From the mean. That's basically what you're looking at, is how far these scores as the average distance from the mean. And that's very important. And we'll have something here. In fact, I might even have it right here. Oh, there it is. Yeah. Okay. Here's your standard bell curve. If you're not familiar with standard bell curves, this is what's called a normal distribution. This is what is expected in most quantitative studies. They think you're going to have this normal distribution. Okay, 0, that's your mean right here. That's whether it's test scores, or age, whatever. Okay, now your first standard deviation, and this number will change. It won't be 34.1. It'll be some number that gets computed. But as you see here, standard deviation, your first standard deviation, and whenever you're dealing with values, whether it's standard deviations or correlation or something, the negative or positive doesn't indicate the strength of it. That's just the direction of it. The absolute value, oops, come back. The absolute value, is that what I want? Oh yeah, it is. I'm sorry. The absolute value is what determines the strength of that, whatever it is, whether it's standard deviation or correlation. So here, whether it's -1 or +1, that's called the first standard deviation. And you see within, like Dave was talking about a second ago, you have that first standard deviation. And look, over 68% of the population will fall in that first standard deviation. IQ scores, the mean IQ is 100. and 68% of the people will fall between 90 and 110. Okay, that's just one test. Okay, let's go to that second standard deviation. Okay, that adds 13.6 to either side. Okay, and what that does is put you out to about 94%, a little over 94%. Okay, I think I may even cheated and figured it out and made a note down here. Hold on, let's see if I did. Yeah, okay, it's 95.4. Okay, so now you're at your second standard deviation. You're accounting for a good portion of the population. If you take it out a little bit more, it goes out to about 98. What did I say? 98.6. Yeah, 99.6. You're getting real close to covering the entire population. And finally, you add another tenth of a percent. Now you're at 98.9. Okay, so this shows you. So when you hear a report this falls, their test score fell within the first standard deviation, they're doing okay. It'd be nice if it was plus, but they're probably still okay. They're close to the mean. Now, in theory, now again, this is in theory, how many standard deviations would you have to go out to get the entire population? Anybody?
4 or more than 4, or is it possible?
That's the right answer, Dave. It isn't possible, because you notice here, like this first standard deviation, that's a huge percentage. It gets a little smaller here, it gets a little smaller here, it gets smaller here. The more you go out, this percentage that you capture will be smaller. In theory, it will never reach 0, because you'll find statisticians and researchers are very wary of the words always and never. Okay. They will usually talk about correlation rather than causality, simply because even if 100% of your subjects responded in a certain way in this study, when you go to relate that to the general population, you cannot guarantee that 100% of the population will feel the same way. Because remember, when you're doing a study, it's an estimate. It's an estimate. And so erring on the side of caution, once again, when researchers and statisticians talk about stuff, they will never say 100%. Because we got up to, 99.8 or whatever in just these 4 standard, 99.8% in these 4 standard deviations. But if we kept on going out, it would get to 99.819 or 99.2 or 99.9999, but you'll never get to 100%. So, because statisticians simply will not go there. Okay, any questions on that?
No.
Let's look at standard deviation here.
Is it always that 68 and 95?
No, it isn't. We'll touch on that in just a second. Okay, computing a standard deviation. I do not expect you to remember these formulas. Formulas are great for figuring things out. If you use them a lot, you'll remember them. If you don't use them a lot, you'll look them up. I'm not doing any research currently, so if I had to start doing my next research project and I had to start computing things, I'd be looking in the book. I don't have enough brain cells to remember all this stuff. If I used it all the time, I would. For the purposes of this course, you might keep some of these handy, but for your final paper, you might want to be able to establish something. But don't go to the trouble of memorizing these things, because for the purpose of this course, it's simply not necessary. And again, if you have a host of resources, whether it's your textbook or a nice website, that'll explain all these. And when you need one, just go to that website or that textbook, say, oh, that's how you figure that out, and then here it is. But anyway, looking at this is the formula for figuring out the standard deviation. Now, something to be aware of: this S stands for standard deviation, as you probably guessed. But standard deviation is also sometimes referred to as capital SD. It is also sometimes depicted as the lowercase sigma. Now, let's not get confused. This is uppercase sigma. Okay, lowercase sigma I'll show you in a second here. Uppercase sigma usually means summation, meaning add whatever follows. Alrighty. So here, for this formula here, basically you're looking at several things. First of all, the S equals standard deviation. Also So it's sometimes shown as lowercase sigma. The uppercase sigma tells you to find the sum of what follows. And the sum is this x minus bar x, where the x is each individual score, test score, age, whatever, and the x bar is the mean of all the scores in the sample. Okay, then you divide that by n minus 1. N, remember, small n is what? It's the sample size.
Sorry, my job is trying to write that answer.
Oh, that's okay. That's okay. Okay, so n minus 1, and we'll get to the y minus 1 in a second here. So, but that's what all those different symbols mean. And I think, yeah, here's an explanation here for you. And S is the standard deviation. Again, the uppercase sigma is the summation, X is the individual scores, bar X is the mean of the scores, and N is the sample size. Now, things to remember. Your standard deviation is an average distance from the mean. That's all it is. The larger the deviation, the more spread out the values are. It's also very susceptible to extreme scores. And if it's 0, there is no deviation. There's no variability. Everybody got a 98 on the test, or whatever the score is. Okay, now you ask why n minus 1. Anybody have a guess?
No.
Okay. Okay. Again, statisticians are making estimates, and when they're taking a limited number of subjects, whether it's 30, 300, 3,000, and trying to take those results and generalize them to the entire population, they don't want to look like complete idiots. Although sometimes they manage to do that quite well. So when they do n minus 1, basically what you're doing there is increasing your returns to be more inclusive. Okay, and by more inclusive, I'm talking about it's called an unbiased estimate. Again, why they termed it that, I don't know. But basically, it's fudging a little, erring on the side of caution, so that you can make the standard deviation a little larger, because in making n minus 1, and going back to the formula here, when you go to n minus 1, that makes the denominator smaller. That'll make this larger. It's just to include a little bit more. They'd rather err on the side of being more inclusive than being, rejecting something that they didn't want to, that they shouldn't reject. And that's basically why you see n minus 1. Sometimes if you're reporting on just the subjects, you might see people refer just to n, but normally in reporting finding, they'll use this n minus 1. Just again, because you're dealing with an estimate and you want to generalize it, you want to give yourself a little wiggle room. All right, moving on to measures of variability. The last one is variance. And when we're talking about variance, what are we talking about? Okay, basically variance is the standard deviation squared. Now, you're probably wondering, well, why do I need to know that? And in some cases, you might not. Statisticians like to be able to describe things in as many different ways as possible in an attempt to find differences, okay? Sometimes they do it in an attempt to understand things better or to make things clearer, and that's the case with variance. Basically, you're squaring your standard deviation, and if you looked at the formula, it's very similar. Okay, here's that lowercase sigma I was talking about. Okay, so standard deviation is the sigma squared, and then you have the summation of your scores minus the mean of your scores squared over the n minus 1, again, the total number of subjects minus 1, and square and all that. So does the symbol look familiar? Yeah, because it's the same one you use for standard deviation. And you're saying, well, what good is this? And that's a pretty good question, actually. While the formulas are similar, the two are quite different. Standard deviation is stated in its original units, okay? And the variance, though, is squared. They squared so you get rid of negative numbers. Your variance will always be in positive numbers. Now, what do you think is easier to interpret when you're looking at standard deviation and variance?
Variance.
Variance. First of all, it's a larger number, okay? That probably makes it the easiest. Plus, you're not dealing with negatives and positives. It's just, you know, you can just look at variance, and the higher the number, the more variance you get, or you have in this. So it's a little easier to understand. All right, this sort of scoops back to some of the things we talked about last week, of the different 4 scales of measurement, or levels of measurement as we like to call them here. You have nominal, you have ordinal, you have an interval, and a ratio. What are the qualities of these different levels?
The nominal for like categories or labeling.
Right. Okay.
Ordinal for ranking.
Ordinal is for ranking. Yeah, very good. Anybody else? Going once, going twice. Okay, interval. It's used to show a continuum, I should say, and it also lets you talk about one score being higher than another. Each interval along the scale is equal to each other. Okay, like on a ruler. Okay, you have, or let me say a thermometer is a better indicator. Okay, you have 32 degrees, which is freezing. You have the 212, and there are points in between. Okay, now when you're dealing with interval, though, the 0 on the scale doesn't mean that there's an absence of the item. A temperature of 0 degrees doesn't mean there's no temperature outside. It just means it's kind of cold. Okay, that's just a point on the scale, and it relates to all the other points, and that they're equidistant, but there's no absolute to it. Finally, in ratio, that's one step further. There's points on the scale, they're equidistant, but they are ratios. You know, inches. 2 inches is twice as much as 4 inches, as 1 inch. 4 inches is twice as much as 2 inches. 1 foot is 12 inches, and that's twice as much as 6 inches. Okay, so there's ratios there. It's characterized by the presence of an absolute 0. 0 on the ruler, that far left edge, that means there's nothing there. There's nothing being measured. It has no length. Okay.
Ratio can't go below 0.
Right. Ratio can't go below 0 because 0 is it. And once you get below 0, you're in, I don't know, somebody's other reality.
You're in interval.
Yeah. Okay. So those you have it. Now, although I have them listed nominal, ordinal, interval, ratio, basically ratio is considered the highest level, and I guess we should do these backwards, but whatever. So anyway, nominal is categories, ordinal puts things in orders, interval shows you, you know, first, second, third, or rather, it shows relationships between things, but there's no absolute 0. Ratio, it puts them in order. It shows a relationship, and there is an absolute 0, and the relationship is everything is equidistant. Any questions so far?
Nope.
Good. Moving right along. Okay, here's a quick breakdown. I'm not going to go through these. We already did. Nominal is categories. Ordinal is orders. Interval is an underlying continuum, and the intervals along the scale are equal to one another. And finally, okay, here's something I want to make sure you understood. We're talking about scale. Scales are marked points that identify the different intervals. And the intervals are the distance between 2 points in a scale. That's something you'll want to remember. And finally, ratio it has an absolute 0 and the absence of any trait being measured. Weight, you know, 100 pounds is more than 50 pounds. 2 ounces is more than 1 ounce. Okay. Okay, so in talking about your findings, any outcome can be assigned one of the 4 scales of measurement. Okay, these scales have an order, as we said, from lower to higher. The higher up the scale, the more precise. And the precise scales contain all the qualities of the scales below them. Okay, moving right along here. Oh, we just went over halftime on our thing here. We're on 53. Talking about reliability and validity. A lot of times people confuse these two things. They are very useful, but they are not the same. When we're talking about reliability, what are we talking about?
Isn't it where, like, if you were going to give a test, if you gave it to another sample, that you would get similar results, that it would be kind of
Yes,
consistent?
exactly. Oh, somebody just scored.
Yeah, sorry about that.
I hope it was your daughter's team.
It was.
Oh, good, good. You're on a team. Okay. Yeah, reliability is it repeatable? Can you take these same results and go someplace else with a different group of people, set up the same environment, use the same treatment, and get the same answers? Okay. So that's what you're talking about when you're talking about reliability. Whether a test measures something consistently is basically what you're talking about. Okay. Here's like you can deal with observed test scores. Now the thing is about reliability. Sometimes absolute reliability is kind of hard to get because they have a thing called the true score, and that's 100% accurate reflection of what you really need to know. And rarely are the observed and true scores the same. Now you might say, well, why is that? Have you ever taken a test when you had the flu?
Mm-hmm.
Did you do as well as if you hadn't had the flu?
Nope.
Nope. Okay. Maybe you go into the room and they have the air conditioning turned up just, meat locker cold, or maybe they don't have air conditioning and it's sweltering hot. Different factors could affect performance on a test or outcomes of any sort of any type of study. And so that's why they say that the true score and the observed score are rarely the same. Now, because you're using assessments, you generally have to settle for the observed score. Although maybe depending on what type of study, if you were studying why maybe there was a new learning system, the students didn't do as well as you think, you could pull in some of the things the conditions that might have affected that true score. You might say the room was hot, nobody got any sleep the night before, whatever. But when you take the observed score, take this true score and the error score, and again, the error score is the difference between the observed and the true. I'm trying to think. I don't recall seeing this a whole lot. Again, it's nice to know that it exists. So if you read about it, the people talk about the error score, it's the difference between what they observed and what the true score was. And if you look, at least in my version of the Salkind book, he shows a graph that shows the difference on a graph. He has one point that shows the true score, and one point that shows the observed score. And of course, the true score is higher, and he has a little line going between the two, and that shows the error score. Depending on what you're studying, you might need to demonstrate that in your findings. For the purpose of this course, you do not. Oh, okay. We talked about reliability, and there's different types of reliabilities. We talked about these last week, so I won't go over them again in great detail. Just to remind you, test, retest. When you want to know whether a test is reliable over time, this is your pre-test, post-test type of situation. Okay. Then parallel or what we call equivalent forms. You take two different instruments that cover the same material and see if they render the same results. Internal consistency. When you want to know if the items on the test assess one and only one dimension. Split half. You take the same instrument, maybe take the odd questions and put them on one sheet of paper and the even on another, and administer that one time to different students and see if you get the same results. Then there's something outside of your instrument that the people who are actually grading these tests or analyzing the results, and that's when you want to know whether the raters are doing the same job. And you have a lot of this in qualitative data when you're like looking at interviews and they're coding the interviews. Well, a lot of times they'll take, okay, here's coder A and coder B and coder C. They do not want them talking to each other. They want, okay, you go through these interviews and you code them the way you see them. And then they'll get together and see where they agree and disagree. And if they all agree and they all say, oh yeah, that person thought this, and I said it was under this category, and everybody else says that, then you have a high inter-rater reliability. Where you have low inter-rater reliability is if one of the raters, or maybe all three of the raters, do not agree on how they coded, how they assigned different categories to the comments made in those surveys. Does that make sense?
Yeah, it sounds like table readings for AP exams.
Yeah, exactly. Okay, anybody else?
Is there one of these that they use more often than the
I would just from what I've read, I bet you that test retest, the pretest post-test probably gets used the most in quantitative data. In qualitative data, inter-rater reliability head over whatever else, over anything else, because that is one of the biggest problems with reliability is if your raters are evaluating things with either personal biases or a misunderstanding of what the rules were, for interpreting stuff. And so I said, for test retest for quantitative data and inter-rater reliability for qualitative data. And that, again, that's a rule of thumb. But just from my observations and readings over the years, I'd say those two are the most frequent you'll see.
That's a good question.
Yeah, real good. Because again, you'll want to know. And talking about, rating things and stuff, you're talking about reliability, and you're talking about reliability coefficients. And really, a lot of this applies to any type of coefficients that you deal with. Okay, when you're talking about reliability coefficients, they need to be positive, not negative. If there's negative reliability, you're back to the drawing board and doing a new test. However, the reliability has a very small, well, I say small scale. It's from 0 to 1. Okay, they don't have to go into big numbers like some of your statistical reports are. And so basically you have a reliability. The closer you get to 1, the more reliable you are. Does it have to be 1? No, it doesn't have to be 1. And depending on what you're studying, that reliability has different ranges, again, depending on what you're dealing with. Validity. Okay, now again, we said they get mentioned a lot together, reliability and validity, but validity is something different. And when we talk about validity, what are we talking about?
Does it test what it's supposed to? Does it accurately test whatever it is you're trying to test?
Exactly. Does it do as it says it's doing? And that sounds simple, but it doesn't always happen that way. Three most commonly types of validity are content validity, criterion validity, and construct validity. Now you'll hear mention sometimes of what's called face validity. And I wouldn't want to rest any of my results on face validity because basically there's no numerical evidence. You're just saying, hey, it looks good, okay? It appears to do what it says it's doing. But if you look at it real close, maybe you discover it doesn't. So sometimes people will refer to face validity, but it's usually to disprove something rather than to say, hey, yeah, my test is valid, I've got face validity. You want to have numerical data that supports your claims for a valid instrument. Okay, when we talk about content validity, what are we talking about there? Anybody? Stumped you. Alrighty. When you have when you have content validity, you want to know whether something truly reflects the entire, I say entire universe of the item in a certain topic. Okay. Basically, you rely on content experts. Do the items represent all the items possible given the questions being asked? And how well do the number of items reflect what was taught? Okay, so basically, is what you have in the test, what you need to have in the test for that test to measure what it says it's measuring. Does that make sense? Snore. Okay, so basically, you're looking at the content and saying, okay, does this accurately cover what needs to be covered in order for this test to be valid, to be assessing what it says it does? Okay, then you have criterion validity, and there's two types. There's predictive and there's concurrent. Anybody want to make a stab at these? Okay, predictive is basically what it's saying. You have some established standards you want to demonstrate, and so you want to see you have these criterion, and basically you're trying to predict what is going to happen. Okay, in the future, will my results reflect what will happen as a base if we take this and throw it out to the general public? Concurrent is what is happening now. Okay, does this instrument actually measure what is going on now? It is actually doing, capturing the phenomena that we're supposedly observing. Okay, does that make sense? Or have I just totally lost everybody? Yeah, maybe I have a cheat note here.
No, that makes sense.
Okay. Oh yeah, here's a little cheater note here that might help. Criterion validity, when you want to know if test scores are systematically related to other criteria, they indicate the test taker. Oops, I can't see what I'm doing here.
So
Anyway.
would an example of criterion validity be when you're asking two questions that should be sort of measuring the same concept and looking for consistent answers from the same respondent?
Yeah. Uh-huh.
Okay.
And okay, again, concurrent is how well the criteria is consistent with what exists in the present, and predictive is how consistent the outcome is what you're predicting to happen in the future. I brought some of these little cheat sheet notes here because they come in handy once in a while. I'm not doing a great job of explaining things, or I don't think I'm doing a great job of explaining things. Anyway, moving right along. Finally, the next thing you have, okay, criterion validity. Here's a little longer explanation here. Again, you want to make sure that the test taker is competent in a certain area, and you want to relate that to the criteria that you've established. Concurrent, again, deals with what's happening in the present. Predictive is what's happening in the future. Okay, finally get back to construct validity. This probably is one, especially if you're doing mixed methods or qualitative type of stuff. Construct validity, you want to establish that what you're setting up in your study, what you're trying to prove, what you're trying to demonstrate as what is happening, excuse me, is actually happening. Construct validity is how well a test reflects an underlying idea, such as intelligence or aggression. They did, at least my version of the book had an example where they had a aggressive behavior test, and the people would take this survey and then they would observe them and see whether out in real life whether these people were passive or aggressive, and if they scored real high on the aggressive test and then they were out and they were being antisocial and maybe getting into road rages and stuff, you could be pretty sure your construct validity was pretty valid, pretty strong. Now, this is probably the most interesting because you're trying to say, okay, do the criteria I've set up relate to the real world? Does this test actually show what's going to happen out there? And consequently, it's the most interesting, but it's also harder to establish because you're taking your data and trying to relate it to real life behaviors, and sometimes that doesn't happen. Some people just take tests differently than they act in real life. Okay, so anyway, talk about validity and reliability. A test can be reliable but not valid, meaning it can be repeatable, but it doesn't necessarily assess what it says it assesses. But it can't be valid unless it's reliable, meaning it can't be an accurate assessment of what it purports to assess if you can't repeat it. If you can only do it once, then there's no way of telling how you got those results. But if you can do it again and again, then you can say, yes, it does assess what it says it assesses, and it will do it every time, or at least a majority of the times. Okay? Does that make sense?
Yes, it does.
Okay. I'm sitting here with my book and my notes and everything, and talking fast and talking fast and thinking slow. Anyway, moving right along here. Now, sometimes, what happens if you can't establish validity? And that does happen, unfortunately. Sometimes you'll do a survey or some other type of instrument. You'll throw it out there. You'll get respondents, and you'll just go and say, this isn't right. Well, there more than one time you'll have to rewrite it. Oh, I'm going to say more than one time you'll have to say, more than one time this has happened. You'll have to redo the test. You'll have to go back to square one. That's why a lot of times when you do studies, if you're doing a real research study, you have to get IRB, approval. But if you're just doing it in class and testing your instrument, you don't. And I would strongly suggest anytime you do a study, do a little pilot test, do a little, amongst friends and family, just to see. Sometimes they'll, that helps because sometimes they'll point out grammatical errors or confusing questions or things. But they could also point out problems in validity because they say, this test was on my understanding of the writing of Edgar Allan Poe, but it talks about Charles Dickens a lot, I think it's not a great example, but it's the only one I got right now. So anyway, and if you have to rewrite, that's when you want to go to your subject matter experts, your contact experts, and have them look at it. In fact, that's probably not a bad idea before you launch the test, just to prevent you from having problems and have to redo things. Okay, a little earlier I was talking about how statistics is just as much a visual science as it is a numerical science. And I probably gave away the answer to this question. Why do we illustrate data? Why give it, graphical depictions? Anybody?
Because a picture is worth 1,000 words?
Picture is worth 1,000 words. That's true. And that's definitely true in statistics. I'll give you some little ideas here. Well, I'll try to give you some ideas if I get my computer to work. There we go. Yeah, visual representation. It's an effective way to examine characteristics. It won't always give you the same detail, but it'll give you a real good, quick feel for what's going on.
I think one of the examples is that it's easier to tell if your data is grouped together or farther spread out.
Yeah.
They lean more towards the high or the low.
Exactly.
Any outliers and so forth.
Exactly. It's a good way of, again, you get an instant snapshot. Again, you won't get necessarily the precision or the detail, but again, if you need to know something like outliers, you see this cluster of scores here, and then there's this one score that's way out there. Okay, well, that shows you. So one of the first things we talk about when we're talking about visual data, we're talking about frequency distributions. And basically, when you talk about frequency distributions, you're basically tallying and representing the number of times certain scores occur. Okay, it says usually, but I disagree with that. He's talking about what he calls interval classes or ranges. You take a survey and what is your age group? 18 to 25, 26 to 35, but a lot of times there are individual, ages or scores or whatever. They don't always put it in groups. The good thing is whether you do these interval classes, interval ranges, or you're dealing with individual scores, a lot of the same rules apply. Okay, now here's for creating class intervals. I'm not going to go into this too great. Basically, they talk about setting a range, and depending on the size of your sample, your range could be 2, 10, 20, could be 5. Again, depending on how many numbers you're dealing with. Select a class interval that will work with the entire range. List the class intervals, and then note the largest interval goes to the top of the distribution. And again, I'm not going to. We'll show that more. Okay, here's our sample frequency distribution. Okay, you have these different class intervals here, 45, 49, and 40 to 44, and so on. And here's the frequency. Here's how often these age groups appeared in a survey or in a test, okay? Okay, so then you'll do one thing you can do with these is what's called a histogram. Now, anybody have an idea what a histogram is? Going once, going twice. Okay, hey, let's just go. And you've seen these in bar charts are basically a form of histogram. Okay, here's the histograms, and basically what you're doing, you're taking your classifications, your ages or your age groups along the bottom here, and say, okay, this group here appeared once, this group here twice, this group, and so on, and you put them in order. And again, you know, if you'll notice here, you sort of have that bell-shaped curve again. Now, again, this is not always going to happen if you're dealing with, you know, age groups and things like that, but for the purposes of demonstration, this is what a histogram is like, okay? Now, something similar to that is something, okay, again, a little explanation. You put your values at equal distance along the x-axis, and then you draw bars or columns from each midpoint to show how often it presents itself, the frequency that it appears in your study. The tally-ho method, basically called because of tallies, and basically it's the same thing. When you have somebody in the 0 to 4 range, you give them a hash mark. 5 to 9, you give them a hash mark, and you can see basically the same data. And you can, again, see that basic bell-shaped curve there. So you have what's called the normal distribution of whatever these are, scores, ages, whatever's. That's called the tally-ho method, just another way of doing things. Frequency polygon, another one here. And here what you're doing is you're taking a point and putting it in the middle of your class, and then doing the frequency. So, and again, you have this bell-shaped curve, and they have it overlaying that histogram, so you have an idea of what they're doing there. But this is all just basic ways of showing you information in a quick snapshot sort of form. Did anybody have any questions or comments?
Nope, I'm good.
Okay, then moving right along. This is kind of interesting one because this is maybe a little harder to understand, but once you realize the concept behind it, it's pretty cool. Okay, here you have your different class intervals here, the different ranges. Now, if you look here, you know, this one only showed up once, this one showed up 3 times, but as this curve gets steeper, it demonstrates 2 things. First of all, you know, it shows that the higher range of things, but it also shows how much that interval contributed to the cumulative, the total number of responses. Because here there's not a whole lot of change, you know, 1 to 4, 1 to 3, and then this goes to like 8. But now all of a sudden you start having higher numbers of higher frequencies, and you can see how that curve sort of shoots up and levels off again. And again, it's just another way of representing data and showing you of how each one of these intervals contributes to the cumulative number of responses. Okay, now there are a couple different ways of depicting data, or you'll see a couple of different depictions of data, and some of the things you'll see when we have these distributions, you'll see things what are called average value, you'll have variability, you have skewness, and you'll have kurtosis. And some of these things, again, these are more tools for you to understand what's going on rather than you to report, you know, the kurtosis of this was blah, blah, blah. You might, depending again on what your study is and who you're journal for. Anybody want to make a stab at any of these? Okay, I will. Oops, average value. Again, average value basically shows what you have here. You have your bell curves again. And in a way, I sort of wish he'd labeled this different and made this the average for C. Oops, didn't want to do that. Average for C, average for B, average for A, because that really leads to grades. You know, sometimes you'll say, okay, the mean for this class was, say if this was C, let's say 75. You see, here's a normal distribution, and it shows you the average value of here. But if you relate to this one, you can see that this class, if this was the people who got Bs, is higher, and C or A, again, flipping these over, is even higher. The distributions are about the same, but the values as you depict them here from again, low scores to high scores, shows you that even if you have a normal distribution within these scores, that you can still have, you know, higher and lower scores and depict them with the same type of bell curve, which might not indicate a huge difference as far as whether these are 75s and these are 85s and these are 95s. It still shows how you have that perfect bell curve within your scores. And I might have a central tendency. I don't want to use that one. Okay, moving right along. No, I don't want to move. Okay, when we're looking at variability, these different curves or lack of bell curves show a lot. Now, if you look at these three here, you have distribution A, distribution B, and distribution C. Now, looking at these, what would you think of, if these were tests, you know, final exams or whatever, what would you think of I would think I would go backwards. There we go. What would you think that distribution A depicts as far as test scores go? Any guesses?
A lot of people scored near the mean.
A lot of people scored near the mean. Real good. Yeah, and you know, it probably certainly more than what your standard deviation, your typical bell curve would do. But yeah, here you have the mean. This middle line is always going to be your mean. And when you have this thing spiking up like that, and then it just falls off real quick, that means, hey, you had a few people got lower than mean. You had a few people get higher than mean, but a lot of people were just right there, close to the mean. Now, distribution B is your typical bell curve. That means you have the normal distribution. You remember the percentage that we said above and below as you go out to the different standard deviations. This is your typical bell curve. What you normally expect. You get some students who do not, you know, get low scores. A lot of students around the mean. Some students above the mean getting the high scores. Finally, you have this distribution C, which would be pretty much the opposite. There's a lot of people that do not score near the mean either. They're above or below. And they refer to these different situations. Well, we'll talk about it in a second. Oops. Okay. When they talk about skew, they talk about the way your curve leans. This also depicts scores. Now, for my money, they got this backwards. Okay, because if you look here, this curve here, that's what they refer to as positively skewed. Now, in my mind, if I was going to positively skew something, I'd be skewing it in a positive direction rather than a negative direction, but maybe that's just me. But anyway, when they talk about a positively skewed sample or depiction of your scores, that means a whole lot of people got on the low scores and then very few got on the high end, okay? Likewise, here's your perfect bell curve. The normally expected number of people got lower scores than the mean. People around the mean, then you have a few that got above the mean. And here you have what is called a negative skew. And here, a low number of people got below the mean and a whole bunch of people got above the mean. Now, looking at this distribution A, the positively skewed, and the distribution C, the negatively skewed. If these were test results, what would it tell you about the test? What was the test for distribution A? What was that like?
Most of the teaching didn't apply.
Most of the teaching didn't apply, or the students didn't do well for whatever reasons. Okay, because you have a lot of low scores, whether it was the material was not presented properly, the students didn't study, it was too hot in the room and they all fell asleep, whatever. Yeah, if you have something like this, that means most of what you were expecting to happen didn't happen. Most students that you thought would do well and get a decent score didn't. Now, the opposite is here. Here, if this was test scores, what would this be?
That it was a really easy test.
It was a really easy test. Yeah. Because you have a lot of scores above the mean. Now, just like everything else in statistics, they have to give weird names to stuff, and kurtosis is no exception. When you have this high concentration of scores near the mean, they call it leptokurtic. Okay, think of leaping. You're leaping up and you're getting a lot of scores near the mean. Then when you have your regular bell curve here, they call it mesokurtic. Think of meso as median, and there's no real kurtosis there, but they call it mesokurtic anyway, just to give you a term. And finally, if you have a really broad dispersion of scores away from the mean, it's kind of flat, plateaukurtic, think of plateaus. So anyway, you have leptokurtic, mesokurtic, and plateaukurtic. And again, this is more for this course. I don't know that, I guess if you wanted to impress people in your journal article, you could refer to the distribution as leptokurtic or plateaukurtic and have everybody going to the dictionary if that's what you want to do. Okay, moving right along, correlations. What are correlations? Anybody? Want to make a stab at it?
Aren't they connections between things?
Yeah, they're connections between things. Remember when we said
between things?
Yeah, relationships. Remember when we said earlier, the statisticians are really hesitant to talk about causality because, can you ever 100% be sure that A caused B? No, but you can always just say there's a strong correlation between A and B, between X and Y, between whatever. Basically, like David said, it's a connection, okay? And you want to establish connections between things. If you're trying a new, asthma drug, you want to have a connection between the improved health of the patients who took it and the asthma drug. And what you do, you have the control group that took the placebo, the treatment group that took the asthma drug, and they get better, and you want to have a strong correlation there. So basically, and correlation is always referred to as R, for whatever reasons, relationship, I guess. And if you see R with a subscript XY, it's the correlation between X and Y. And as Dave said, it examines the relationship between two variables. This relationship can range from -1 to +1. Now, it's the value of the correlation that depicts the strength, whether it's 1 or 0.5 or 0.75. Don't make the mistake of thinking because it's negative, it's a weak correlation. It just shows what direction that correlation is going, okay? But it can go from -1 to +1, and you will very rarely see it at 1, okay? And basically what correlations are doing is showing how the change in one variable is reflected in the other variable. Now, they have things called bivariate correlations where you're testing two variables, and then you have the Pearson product moment correlation, also referred to as Pearson's R, that examines the relationship between two or more continuous variables. Okay, when we say you have a positive correlation, what are we saying?
There's a strong relationship?
Well, not necessarily. It could be a weak relationship, but it could still be positive.
Is it the way that it's depicted in a graph?
There you go, or depicted in the findings, or however you're depicting it. Basically, an increase in one equals an increase in another. Let me see. I'll show you something here in a second that'll demonstrate. But basically, as A increases, B increases. Okay, as you get older in school, you know more about math. Okay, so basically, it's a positive correlation. The increase in A equals an increase in B. Okay, then you have negative correlations, and as you would probably gather, that means the exact opposite. The more you increase A, the more B decreases. The more weight in a set of barbells, the fewer times you'll be able to lift them. All right, so you have positive and negative correlations, and depending on what that correlation is, the strength of them is not in the positive or negative, it's how close or how far away from one those correlations get. Okay, positive correlations are also called direct correlations. And again, when one variable increases, the other variable increases. Negative or indirect correlations, when one variable increases, the other decreases. Things to remember about correlations. Again, they range from minus to +1. And again, it's the absolute value, how close they get to 1, that indicates how strong they are. They suggest using indirect and direct instead of positive and negatives, just so you don't confuse them with strength or the value of the relationship. then again, the Pearson product moment, the Pearson R correlation is represented by the small r with a subscript to represent the variables that are being related. Okay, let's look at, what do we have here? These two graphs. What do they show? What kind of correlation?
Positive.
Yeah, that's a positive correlation. You can see how stuff is sort of moving in a general upward direction. Okay. Now this one here is called a imperfect correlation, because you can see it goes in the general direction, but it's sort of scattered. This is a perfect correlation here. I mean, it's just a straight line. Okay, everything is 1 to 1. Whatever this is, as this increases from 1 to 2 to 3 to 4, the frequency or the value also increases from 1 to 2 to 3 to 4. Okay, and this, I'm not saying you'll never see that. It's kind of rare, because usually you'll see something more like this. Okay, now on the flip side of that, oops, where did I go here? Okay, here's a strong negative relationship. You see, it's a sort of a downward direction. Oops, the whole thing's going away. Downward direction of your correlations. You see here, as this increases, okay, here whatever 3 was, 3 pounds, they were able to lift it 9 times, but 4 pounds they were only lifted 5 times. And sometimes it's not going to be, again, a straight, 1 to 1 correlation. It'll scatter around, but you can see the general downward trend, and that's what's called a negative correlation. Rule of thumb, okay, how do you figure out whether your correlation is strong or weak and stuff? They have a gut rule of thumb here, and you can see what those levels are. Different correlations, depending on what you're showing, may not need to have a strong or very strong relationship to be significant. But again, this table shows you just general guidelines for correlation, how to interpret them. Okay, and then you also have a thing called a curvilinear relationship. Any thoughts on what we mean by that? All right. Bang.
Where it's not positive or negative, but yeah.
Yeah. See this here? This is a relationship between age and memory. Okay. And you see the 5-year-old, not much memory, and if you have a 5-year-old, you'll know about that. Then as you get 10, it gets a little better. 15 gets better, and 20 and 25, and it gets about 35, and it keeps on getting better. Then you get to 40, and the memory starts fading. And 45 to 50 starts going down. So this is called a curvilinear relationship, because that shows you how something changes over time or over distance or over some stretch, some continuum.
So in this case, they're increasing to the middle. Do they ever start high and decrease to the middle and then increase again?
That could happen, but then it wouldn't be a curvilinear relationship. It would be a negative relationship. Okay, if you start high and then work your way down.
If you work your way down and then back up again, though.
Oh, I suppose you could, sure. Yeah.
Turn that frowny face upside down.
Yeah, but I'm trying to think of how that might happen. Maybe if, let me see. I don't know. I was thinking
possibility for caring for yourself.
Yeah, maybe I was thinking of something extreme, like maybe a cancer patient, as they, when they, just before they go to chemo and they're going through chemo and then they come out of chemo, the ability to do something, it would weaken at first as they went through the chemo, and then as they recovered, they would get stronger. And then, and maybe that's not a great example, but that's the only way I can think of something like that happening, where you'd start out okay, get worse, and then get better. Unless it was, somebody who tracking, they were, well, I'll tell you what, let me just, I'll probably be sorry to do this, but anyway, let's just flip this around for a second. Let's say, again, let's forget memory for the moment. Something like that. Maybe someone like me, okay, I'm 67 years old, and I'm saying, man, I'm getting overweight, so as I get older, I start exercising more, but I don't start exercising, but I keep on going to buffets all the time. And then one day I said, man, I got to stop. I got to start exercising. I got to get better. And so as I get on in years, I start exercising and working out, and then I get better and better and better. So I said, maybe that's not a great example, but it illustrates the point as how that.
But it still would be a curvilinear.
It'd still be a curvilinear. Anytime you have that curve, it's called curvilinear. Okay?
Yep.
Any other questions?
Mm-mm.
All right, moving right along here. We're almost to the end. Okay, other correlations. There, you'll hear some you'll deal with here, some you won't deal with, but some of the other correlations you'll have are regressions, and you probably hear about linear regression, ANOVA, analysis of variance, and chi-square. And regression is when you want to use correlations for one data set to predict correlations in another. Okay, you've tested the book I have gives an example where they compared high school GPAs to first year college GPAs, and they established, okay, the class of 2017, there was a correlation between the high school and college GPAs, say it was 0.9. Okay, based on that, we're going to predict the 2018 graduating class will have a 0.9 correlation between their high school and college graduations, or college GPAs, I should say. Whether that works out or not, you know, that gets revealed in your study, but that's what regression does. Next is ANOVA, or analysis of variance, and that's what you do when you test more than two groups and compare their average performance. Okay. And finally, the chi-square is a non-parametric test. Remember when we mentioned non-parametrics? It's either there is no standard distribution, there is no bell curve, or you don't know what that distribution is going to be. And basically, it's a way of testing, because you don't know what you're dealing with. It's a way of testing whether the distribution you observe is what you expected to occur by chance, or whether there was something that influenced that. Okay? I think.
Right.
Oh, that was slide 101. Oh, very good. Any questions about anything?
No, I don't have any.
Okay, just as a word of whatever, the upcoming quiz, all the answers were contained in tonight's talk. So if you want to go over that again and look at it, you might want to do that, or you might not want to. Anyway, this worked out real good.
Is there any way to open the quiz early?
No.
Just because we're going out of town on Sunday, and I don't remember when it was.
The Sunday, it'll be open Wednesday through Saturday, or Thursday through Saturday. So you're good. You're good. Yep. And next week, what we'll do is we'll basically do an overview of Module 3 and the assignment for that. And then the following week, I'll do what I did tonight, just a review of everything in Module 3. And do any of you have any questions on the assignment that's due or anything like that? Okay. Well, again, if something pops up, you can always email me. I'm you know where to find me. Oh, Kara's car got hit. Okay, well, she's dealing with traffic problems here. Sorry, Kara. And let me see. I'm going to have to. Okay. I think we've. Oh. Okay, good. Here's something from Megan. Anyone who hasn't done the readings yet and have the 5th edition, the 6th chapter seems to be matching the chapter for this week. Oh, good. Well, thank you, Megan. And I think that's all the comments we have. Okay, folks, as I said, if you have questions about the assignment, it's due Wednesday. The quiz will be open Thursday through Saturday. And thanks for coming tonight. And I'll look forward to reading your papers, your critiques. And again, if you have a question, feel free to give me a call. I'll take care, and I'll see you next week. Bye.
Thank you. Bye-bye.